Chapter 18, Air Pressure and Wind. This is the first chapter in Section 2, which also includes Chapter 19 and Chapter 20. So first let's talk about what is air pressure, also known as atmospheric pressure. Atmospheric pressure is literally the force exerted by the weight of the air that's above you at any given place in time. If you start at sea level and start to move up a mountain, as you increase in altitude, the air pressure actually decreases because there's now less air pushing down from above you. We often don't feel this if we just walk from maybe the first floor to the second floor of a building, but we do feel this in certain circumstances. You might feel it if you're going up into an airplane. Even though they pressurize the cabins, some of the air pressure still changes, and you have to equalize what's within your ears and outside your ears. That's why they pop. The other time that you experience this is if you climb a tall mountain. You can feel winded, or it might feel hard to breathe at the top because there's literally less air, less molecules moving around in that certain area of space. Additionally, another example of this would be baseball players who have a lot of home runs in an area such as Denver, Colorado. The air pressure is less up there, so it takes less pressure pushing against the ball to move it through the atmosphere when there's less molecules there. So that's why you end up having more home runs in areas such as Denver. You can also experience it if you are dealing with alcohol, because your blood alcohol level is all a proportion, and with less atmospheric pressure it actually changes the amount of alcohol to blood ratio, and you can get intoxicated much faster. We measure atmospheric pressure in either millibars or inches of mercury. As you see in the image over on the right, it's showing a way to measure the atmospheric pressure pushing down. Imagine that this tube was at one point flipped the opposite way and it was completely full of mercury. The tube is then immersed and inverted into this container. And the container is also filled with mercury. But the mercury, some of it will be pulled out due to gravity out of this tube, while air pressure is acting opposite and pushing down on the mercury. This causes some of the mercury to move out, but not all of it, and the tube is still mostly full of the liquid. However, up here you get this vacuum of space. This allows you to measure how much air pressure is pushing down as compared to how much mercury has been moved downwards. In this vacuum of space, it's not air, it's literally nothing. It's emptiness. The way that we measure air pressure is by using a tool called a barometer. We can either use a mercury barometer that was invented back in 1643, which is basically the instrument that you saw in the previous slide, of course more contained, or you use an aneroid barometer, which does not use liquid. Instead, it uses a chamber that expands and contracts with the changing of air pressure. You can also use a baryograph, which continuously records the air pressure, so you can have a record of how the air pressure is going up or down, and this way you can tell changes throughout time. The top right picture is a typical face of a barometer that you might see in a household. Since most people do not know what different air pressures actually mean, they've put these terms on here: stormy, rain, change, fair, very dry. These storms don't always match up, but in general they coincide with the air pressure, so that when a user is reading this type of instrument they can kind of tell what's going on in the atmosphere. The next thing to talk about is wind. Wind is literally just the horizontal movement of air. We all commonly know what wind feels like, but when you actually define it scientifically, it is that horizontal movement of air. But there are certain things that control wind, and the main force that controls wind is the pressure gradient force. This is when you have a high pressure area in one location and a low pressure in the other. When you have something of high pressure, it wants to move away from that area. It's pretty much filling up, and in this case, the air will move away from a high pressure area and move into a low pressure area. On this map below, you can see lines that map out where the different pressure systems are. These lines are called isobars. And then the space between the isobars can show you how drastic the pressure gradient is. If the isobars are further apart, the pressure change is more gradual. When the isobars are close together, such as over to the right of the picture, encircling the L, which stands for low pressure, this means that the pressure gradient is very steep, and the wind will be moving much faster in this situation. It's kind of similar if you ever look at a topography map, where you're looking at the lines showing altitude. And so any of the areas that have the lines close together, they're steep, so that would be an area that has a high mountain peak on it. In this picture, you would typically find the wind moving from the high pressure area in blue towards the low pressure area in red. Another type of control on wind is the movement of our Earth. As the Earth rotates underneath us, it changes how the wind moves, since the wind is not directly attached to the surface of the Earth. Therefore, while it does move along with the Earth slightly, it doesn't move with it as directly as, let's say, the mountains move with the Earth. This effect is called the Coriolis effect. It causes an apparent deflection in the wind direction due to the Earth's rotation. In the northern hemisphere, this happens to the right, and in the southern hemisphere, it happens to the left. In the picture over on the right, the top picture shows a non-rotating Earth. In this situation, let's say we wanted to launch a missile from the North Pole at 90 degrees longitude and hit the equator at 90 degrees longitude. In order to do that on a non-rotating Earth, you simply have to set your trajectory straight. However, since the Earth is rotating underneath us, if we set the trajectory straight, by the time that missile reached the equator, it would no longer be over 90 degrees longitude. Instead, it would be over 105 degrees longitude, deflecting it to the right from the position of where it was thrown. It's kind of like if you think of a treadmill. If a treadmill is moving underneath you and you jump up, you don't move back with the treadmill. Instead, you stay in the same place while the treadmill continues to move under you. When you land, if you had numbers or something written on the treadmill, you would see that you landed at a different spot than where you started. The next control on wind is friction. Air in the upper atmosphere, which is not really talking about air really high up, like in the thermosphere where we were talking about the different spheres of the atmosphere. When we're talking about these types of controls, air pressure and wind, we're primarily only talking about air in the troposphere, that first layer, before you hit the ozone layer. So we're discussing air in that troposphere. The air, the upper air winds, this is what you would typically think of as the sky, or where you might see the clouds. This air does not come in direct contact with the Earth, therefore there's no friction along with the Earth. This air is controlled by the Coriolis effect and the pressure gradient. The air in the upper atmospheres can move almost like a river. An example of this is the jet stream, which passes from the US to Europe over the Atlantic Ocean. This was an important discovery for pilots who were trying to cross the Atlantic to save them on time and save them on fuel. Then we have the atmosphere that is all around us right now, the surface winds, the ones that we would feel when we're standing on the surface of the Earth. Anything that is not too high off the ground. These winds interact with the surface of the Earth, and that surface of the Earth ends up causing them to slow down due to friction. Just as if you rolled a ball along the surface of the pavement, it would cause the ball to eventually slow down due to the friction. Well, you see on the right-hand side that the lower picture shows that the surface wind is affected by friction, Coriolis, and pressure gradient, and the upper winds are only affected by pressure gradient and Coriolis. Since we're not in a physics class, we won't have to map it out. You just have to know that the surface winds actually have an extra component controlling them. Some terminology with high and low pressure systems. Low pressure systems are called cyclones in the northern hemisphere. A cyclone in the northern hemisphere also is associated with rising air. Since the pressure is not great, it's not pushing down, there's room for air to rise upwards. This causes clouds and precipitation to occur. Also, since air is typically moving out of high pressure areas, air moves into low pressure areas, causing winds to converge. Again, this converging air then rises, causes clouds and precipitation. The other system is called an anticyclone in the northern hemisphere. It's a center of high pressure. High pressure has a lot of air pushing down on it, therefore the air is sinking. When the air hits the base of the earth, the surface of the earth, it has nowhere else to go, so it must spread out or diverge. Since the air is sinking, it tends to bring in fair weather, meaning that since rising air causes clouds, sinking air causes clearer skies. And this is the flow that's associated with it. It kind of acts, again, like a conveyor belt. Air will sink. Aloft just means upper atmosphere. So air at the upper atmosphere is coming together so that it can sink down and cause a lot of pressure pushing down on this high pressure location, or the anticyclonic flow. Since there's nowhere to go, the air moves outwards. It diverges all out in all these directions. Eventually, it ends up coming in contact with a low pressure system. At the low pressure system, the air moves inwards or converges. Since it has nowhere to go, it starts to rise upwards. Once it rises up and hits the upper atmosphere, it also diverges outwards. And it goes in this direction too, so that it then creates this circle or this conveyor belt that goes around and around and around. So basically the high pressure systems at the surface will feed the low pressure systems. Next, we're going to talk about a concept of the different atmospheric cells or convection cells that occur along the globe. We're going to look at this globally, so we're not going to really take into account any of the oceans or the continents at this point. We're going to talk about two types of globes that we could have. We could have an idealized globe, or what we really have, which is a rotating globe. First, we have the idealized global circulation. In this situation, you would have one convection cell in each hemisphere. What would happen is all the sun would be pointing at the equator, leaving the poles to be cold. At the equator, you would have hot air. The hot air would rise, producing a low pressure system. The air would then move outwards and move towards the poles, where it would sink back to the surface, causing a high pressure system. As it sank back to the surface, it would then move back to the equator until it heated up and rose again. This creates one cell in each hemisphere. However, our Earth is rotating underneath us, as we already talked about with the Coriolis effect. This rotating Earth causes us to have 3 convection cells in each hemisphere instead of only one. This is the realized, or the actual, or what's actually occurring. This is how our global circulation systems look. You still have most of the sunlight coming in at the equator, which heats up the atmosphere, causing the air to rise, causing a low pressure at the equator. As that air rises, it ends up starting to move outwards. And because the Earth is moving underneath us, underneath the atmosphere, the air starts to pile up right around 30 degrees in the northern hemisphere and in the southern hemisphere. It starts to pile up, so it sinks back down and it causes a high pressure system. That air then moves outwards in both directions, north and south. Eventually, it starts to pile up along 60 degrees latitude, north and south. When it starts to pile up, it starts to rise, again causing clouds and precipitation. This air then merges outwards until it gets to the poles. When it gets to the poles, it sinks back down again, causing a high pressure system. This causes us to have an alternation, high pressure at the poles and at 30 degrees, and low pressure at 60 degrees and 0 degrees. This causes 3 convection cells in each of the hemispheres. The main cause for this is the Coriolis effect, causes buildup of pressure at both 30 degrees and 90 degrees. This results in surface winds. We end up having surface winds that go from 30 degrees back down towards 0 degrees, from 30 degrees up to 60 degrees, and then also from 90 degrees down to 60 degrees. The ones between 0 and 30 degrees are called our northeast trade winds. The ones from 30 up are called westerlies. And this is when you're looking in the northern hemisphere. The directions switch if you're looking in the southern hemisphere. Winds are always named from the direction that they are coming from. So the northeast trade winds, you see they come from the northeast, flowing downwards. Our westerlies are often interrupted by cyclones as they're coming across the Atlantic Ocean. The northeast trade winds are named because they actually aided in foreign commerce. They helped, just like the jet streams helped with pilots making it over to Europe, they helped with commerce coming from Europe over to the Americas. And so it helped to, again, decrease the time that it took to travel and also increase the efficiency of getting there. So that's how our Earth is, how our winds move around globally. However, you probably know, just similarly as you know that latitude is not the ultimate reason that we have temperatures in certain areas, we also can experience different types of winds from one regional location to another. So on a smaller scale, what affects atmospheric circulation? Or basically, what else affects winds? You probably often know that standing on a certain side of a building will make you less windy, or standing on the other side of it, you'll have a really, really big windy draft. But what else actually affects the wind on a smaller scale? First one is very similar to the land and sea that we talked about when we were looking at temperatures. Just like the continent, just similar with the wind, continents and sea cause different winds to occur. And it's based back to the fact that there's seasonal temperature differences. This is more obvious in the northern hemisphere because the northern hemisphere again has more land. We saw this in the lab the other day. In general, you can see that in January you have a lot of high pressure systems. In January, in the northern hemisphere, the continents are colder than the water. This causes more sinking air over the continents. That causes high pressure systems. In July, the continents are warmer than the water. The warm continents causes the air to rise, causing low pressure systems. You can see that the pressure over the oceans doesn't change too much from season to season, but the pressure over the continents changes drastically. One event that's caused by the continents versus the seas is an event called the monsoons. These occur over continents due to the change in pressure, and they bring rain and floods into an area. In the winter months in India, you can see that a high pressure system caused by the colder continent, colder landmass, causes sinking air. The sinking air then diverges out, causing drastic winds and causes a dry continental area. During the summer months, the continents heat up, causing rising air. Therefore, air and wind rushes in from the Bay of Bengal and the seas, causing a wet environment and also cooling down the location. This can cause lots of flooding and lots of rain to occur. Down the bottom where it says monsoon, that's actually there's actually a lot of stuff you can look up online to see the drastic effects of a monsoon. And they cause extreme amounts of water and extreme amounts of flooding. Another thing that can happen is we can have local winds that occur. And these are just winds that are on the small scale. They're produced from temperature differences. Again, we can see that the land and the sea changes temperatures and can cause different winds. On the left-hand side, you see a daytime sea breeze. If you've ever sat on the beach during the day and you felt kind of cooler than we were when you were on the street, that's because you're experiencing a sea breeze. The cool waters causes the air to sink down towards the water. At the same time, the hot land causes the air to start to rise, creating this convection belt. So as the air sinks, it has nowhere to go, so it starts to move to this low over here above the land, and then the air rises and moves around. And so it keeps moving around, and it causes you to feel cooler if you're sitting right here on the land. Additionally, since the air and the sea act differently in retaining heat throughout the night, you can see that you end up having the opposite effect at night. You have a land breeze. The cool land causes high pressure, and then the air will move off to sea. Sometimes you might get this inversed even during the day. Often when you have it inversed during the day, it tends to bring in bugs from the inland areas. You'll hear people say, oh, the mosquitoes or the flies were so bad. They're probably experiencing a land breeze during the day. The next types of breezes are mountain and valley breezes. Remember, winds and breezes are named from the direction they come by. Valley breezes are winds that move upward from the valley up the side of the mountain. This can occur because the ground is starting to heat and the winds start to move up. During the night, mountain breezes occur. Air starts to cool down and starts to move downwards down the mountain. This can sometimes be detrimental for crops if it moves down and kills off crops. Another specific local wind is called Chinook winds or snow eaters. Wind is coming over a mountainside. It doesn't have any precipitation in it because it lost it on the other side of the mountain. As it's moving down, it's heating due to adiabatic heating. So it's heating at that dry rate that we talked about the other day, even though this does say something slightly different. But it's heating at that dry rate that we discussed. As it's heating the ground, and it technically starts to eat the snow or melt the snow. And so it causes a melting of the snow, a change in the climate at that moment. The next local wind, a very specific one, is the Santa Ana winds. Out in California, these are very common. What happens is the winds will move over an area. As they move over, they lose all their moisture. The moisture is expelled out of them, and so you have these very, very dry winds that move through. I've heard that your lips are so dry and peely and chapped when these come through because all of the water is evaporated out of your body to fuel these dry winds. In addition, it dries out any of the vegetation around, which ultimately fuels the fires that are common in California. So how do we measure wind? We talked about barometers for measuring air pressure or atmospheric pressure. But we can measure wind with tools also. We first can measure the direction of wind, which we talked about, that wind comes from the direction, they're named for the direction that they originate from. You can also either describe them as a compass direction, north, south, east, west, or a degree, so coming from 0 degrees all the way up to 359 degrees. The tool we use is a weather vane. You can see on the picture on the right, I'm not quite sure if this picture uses the shark's nose or the shark's tail fin to show the direction of the wind, but basically that north, south, east, and west compass stays fixed, and whichever way it points you'd be able to tell which direction the wind is coming from, and you'd have to look it up on the instruction manual. The other thing we measure about wind is speed, and we use an anemometer. And there are two types. The first picture there in the middle is a cup anemometer, and you can also see that it has a weather vane attached to it. Basically, it acts sort of like a pinwheel, and as it spins around, it either spins fast or slow depending on how much the wind speed is. You can see on the right hand side is one that's a more electronic, handheld. Also, again, it looks like a pinwheel, and as it spins faster or slower, it'll give you a wind speed. It's basically like your RPMs in your car. So, wind direction. We know that winds move from high pressure areas to low pressure areas. And when they're moving, this produces changes in temperature and also changes in precipitation. One major event that occurs due to change in winds is the El Niño, La Niña, or the Southern Oscillation. El Niño is the process in which winds flow southward along the coast of Ecuador and Peru, which are over in South America, right about here. This causes warm water to occur in the areas, and it causes a sinking of the heavier, denser water. This warm water ends up being produced, and it doesn't allow nutrients to come into an area. Warm water doesn't hold as much nutrients as cold water. When this water comes in, it stars the anchovies, which has been typically known to be a problem in Ecuador and Peru. Fishermen are pretty used to it. They'll take that time to fix their boat. But what's happened in recent years is it's become heavier and heavier and worse, and it's been starting to cause problems in other areas of the world. So due to this warmer water and heavier rain, because the warmer water will cause the rain the air to rise, you'll end up having more rain. But then it affects other areas of the globe too. Over in Africa, you get more heavy rains. But in India and Australia, you end up getting a lot of drought. Then we have the opposite situation happen, which is called La Niña. El Niño often happens around Christmas time, so it's given the name due to El Niño meaning the boy, and La Niña just is the opposite, so La Niña means the girl. And in this situation, cooler water comes into the location, and drought conditions occur. And drought conditions can occur all the way up into the U.S. And then you also have drought in Africa, heavy rains in India, and heavy rains in Australia. And this is actually occurring right now. We're experiencing the events, and we are actually experiencing a warmer area, but areas such as Oregon and Washington are experiencing colder events. Down on the bottom here, you can see there's a URL for a news report about it. If you're interested, you could go and watch it. It was from, I can't remember what year that was from, but it was from a while back. Basically, this is all related to the large-scale atmospheric circulation. The Southern Oscillation is the changing in the pressure between the Eastern and the Western Pacific. They also think there might be a North Atlantic Oscillation, but it hasn't quite been studied as much yet. So if you go back to this last slide, it's that change in pressure from the East Pacific and the West Pacific. You can see it a lot here, the change in temperature on the East and the West. Our strongest El Niños that we ever had recorded were in 1982, and then since it happens in Christmas, they often get, bootstrapped over both years, 1982 and 1983, and then also 1997, 1998. And this caused rains in Peru and storms in California. The 1982 El Niño is when we really started to realize that El Niño and La Niña are major global events. Before this time, it wasn't as severe. It still occurred, usually on a certain cycle, but it wasn't as drastic, and we didn't notice, or we didn't have the technology to really figure out why things were occurring globally. But in 1982, we realized that this was not an isolated event that just caused problems for Peru and Ecuador, but it caused problems worldwide. And now, with events such as global climate change and increase in temperature, we're often seeing El Niño and La Niña occur more frequently and more dramatically than they used to in the past. So how does pressure affect our precipitation? Well, when we have high pressure systems, which we saw over a lot of continents, you have sinking clouds, which causes less rain. This happens in our desert areas, such as the Sahara, the Kalahari. When you have low pressure systems, we said that's going to cause the air to rise, which causes clouds and more rain to occur. This tends to happen over Amazon and Congo basins. And then we already saw how land and water can affect pressure systems on a small scale based on the coastal areas. But in general, where you have large land masses, you have less precipitation in the center, which often also relates back to our desert areas. Another thing that can happen is that mountains can act as barriers to the precipitation. So while you might have a lot of precipitation in Seattle because you have water directly to the west of it, you don't have as much precipitation on the other side of the mountain barrier because the water can't make it over there. And that is my winded Taylor ham, all tired out from a day of fun. This is the end of chapter 18, and we will go over a lot of this stuff in lab too. And I will talk to you again on chapter 19.